Hey guys. So today today's Tuesday. You had your test yesterday or your quiz yesterday. I hope it went well. We have a test next Monday on sections 2.5 through 2.7. So I think this is the shortest test of the semester. And I will be ready for you at 8:15 a.m. If you do want to start, that's optional. We're going to see each other on Wednesday. So I want to spend that day going over your quiz from Monday and then doing a test review or any questions that you may have from the test from sections 2.5 through 2.7. And then Tuesday and then Thursday and Friday will just be devoted to sections 3.1 and 3.2. The homework for those are already out, so please take some time to finish those homework assignments. Okay. Okay. We have parabolas. Section 3.1 is about parabolas. And I know you're familiar with this. This graph is taken from your textbook on page 347. But parabolas are these horseshoe-looking things. They are always symmetrical on what's called their axis of symmetry, which would be a vertical line here, since we're talking about functions still. And every parabola has a vertex. The parent function of a parabola will have a vertex at 0, 0, but with transformations, they can be shifted left, right, up, and down. And also with transformations, they can be flipped upside down when the a value is negative. So the a value is the value in front of the parabola when it's written out explicitly in front of the x squared. So for example, here's a parent function y equals x squared. So it has a vertex at 0, 0, and it happens to contain this point 3, 9. If you 3 squared is 9. So here is g of x, which is a parabola because I've got this square right here, but it's gone through lots of transformations. Now I put some red and some blue. Why is that? The blue is the only transformation that affects x. So this x plus 4 being inside the grouping symbol before the squaring occurs means it's going to move everything to the left 4, including the vertex. And the other 3 transformations all affect the y value. So first, the multiplication. So -3. The negative multiplies all the y values by a -1, which means it would graphically would flip it upside down. So the parabola would be facing down here. The 3 multiplies all the y values by 3. So it gets stretched vertically. And then last, this subtracts 9 from all the y values. So you put them all together, the vertex would now be -4, 9. You could see it in here. So this is to the left 4, and this is down 9. So the vertex is -4, 9. And 3, 9 got converted to -36 from this. First, move the x value to the left 4. So if you move 3 to the left 4, you would get -1. And the y value, 3 things happen to the y value. You triple it, so 9 becomes 27. You take its opposite, so 27 becomes -27. And then lastly, you would subtract 9. So -27 minus 9 brings you to -36. And of course, if you just plug in -1 into here and evaluate, you would end up getting -36 anyway. Some quick ones here. So here you have 4 parabolas. This parabola, the axis of symmetry, well, let's do the vertex first, actually. The vertex, this went to the right 1 and up 3. So the vertex is 1, 3. The axis of symmetry goes right through the middle, right, which would be through the vertex. So the axis of symmetry is x equals 1. It's always the x value of the vertex. Here, the vertex is -8, 0. Didn't go up or down at all. -8, 0. And the axis of symmetry is x equals -8. Both of these are facing up because the a value here is +1. Here the a value is +2. Since the a value is positive, it's facing upwards. This one, the a value is -1. This is 11 minus x plus 2 squared. So the a value is negative, so this one's facing down. but what is the vertex? Notice 11 minus this, I could rewrite this with the 11 on the right side. I could write it as negative x plus 2 squared plus 11. That would be the same thing as what you see here. So the vertex is negative 2, positive 11, which makes the axis of symmetry x equals negative 2. And then here, this one, you could mentally subtract 4 to have it solved for y. And you have negative 3x squared minus 4. Well, there was no movement left or right. So the x part of the vertex is 0. But it did move down 4. So the vertex is 0, negative 4. Axis of symmetry is x equals 0, and this one faces down because a is negative 3. What is the vertex of this? What is the axis of symmetry of this? And what's the domain and the range? Well, this one looks a lot different than these. Here, it was more clear to see the movement left or right because it was parentheses squared. It was the transformations were kind of obvious, but now it was all multiplied out and simplified. This is what some people call standard form. So how would you find the vertex of this? There is a way. It is the opposite of b over 2a. So negative b over 2a. You let the x value equal negative b over 2a. That will be the axis of symmetry here, which is also the x part of the vertex. So where did this come from? There are two defenses. Negative b over 2a. The algebraic reason is much more convoluted here. Here's ax squared plus bx plus c. I'm going to go through this quickly. This is any quadratic. As long as a, b, and c are real numbers, this is any quadratic. I'm going to complete the square. So I'm going to subtract c on both sides. Now divide by a on both sides. And then this binomial here, I'm going to add something so that I complete the square. It's half of this squared. So half of b over a is b over 2a. And if I square that, I get b over 4a squared. So I add that to both sides to keep the balance. And then, now that I've completed the square, I get to reap the reward. This is a perfect square trinomial, so I can factor it. It factors into x plus b over 2a squared. And solving for y, I can multiply both sides by a. So an a would get attached to this term. And then in the second term, these two a's would cancel out, leaving me with this. You add c, and you get this. So hopefully you could kind of see in here this y equals a times x minus h squared. This is a common way to write this vertex form, plus k. So the k would be the movement up and down. The h would be the movement left and right. The a, of course, is the vertical stretch. It's the same a as the original a, and ax squared plus bx plus c. But you could see that the movement, the left or right movement is h, and this is where this b over 2a comes from. And the opposite because if h is positive, this would be to the right h units. The calculus way, I think one of you took calculus, but next year or sometime soon, taking calculus is real fantastic. So the derivative is basically the how the function changes over time. The derivative of this function is 2ax plus b. And if you set that derivative to 0, you're basically finding what x value has basically a slope of 0, has no change whatsoever. And that part would be the vertex of the parabola. The vertex of the parabola is when no change is occurring. Here, the change is increasing. Here, the change is decreasing. But at the vertex, there is no change. So you set that equal to 0, you solve for x, you get negative b over 2a. So that's all kind of defending why negative b over 2a even exists. But just something you need to remember. It'll help you find the axis of symmetry for any quadratic, which in turn will help you find the vertex for any quadratic. So back to this one, 2x squared plus 8x plus 10. I'm going to find the axis of symmetry first by doing negative b over 2a. Plugging and chugging, that's negative 8 over 2 times 2, which is negative 8 over 4, which is negative 2. So the axis of symmetry is x equals -2. That'll help me find the vertex. Since -2 is the axis of symmetry right there, it's going right through the vertex. So that means -2 is the x value of my vertex. And by plugging -2 into the function, I will find the y value. So I evaluate, and I discover that +2 is the y value, which means that the vertex of this parabola is -2, 2. And what else? The domain and the range, well, the a value is 2, which is +2. So it's greater than 0. So this parabola is facing upwards. So since it's facing up, it must have a minimum. And the minimum occurs right at the vertex. The minimum y value is 2. And every other y value is greater than 2. So the range is from 2 to infinity. The domain for all parabolas is all real. The domain, there's nothing stopping you from plugging in an x value. You're not dividing anything, so there's no threat of dividing by 0, and you're not taking the square root of anything, so there's no threat of taking the square root of a negative. So the domain of here is all real. And incidentally, 10 is the y-intercept. That's always that should always be flashing through your mind. If you plug in 0 for x, these two disappear, and all you're left with is 10. So the y-intercept is 10 here. Can you graph this by just using the vertex and x-intercepts? Yes, I can. By the vertex, I'm using -b/2a again. So -b/2a results in -4.5. That's just the x value of the vertex. You have to plug that in to find the y value of the vertex, get those calculators out, and you discover -12.25 is the y value of the vertex. So the whole vertex is -4.5, -12.25. So I would graph that. -4, here's -5, here's -6, here's -4.5, and I'll do my best to find -12.25, somewhere around there. What about the x-intercepts? The x-intercepts are when the function equals 0. Those are the x values that make it equal 0, also called the zeros. And this harkens back all the way to one of our first days together in our first unit. So there's lots of ways to solve this. You could solve this quadratic formula, complete the square root property, but factoring, if you can factor, that's usually the fastest. So this does factor to x plus 8 and x plus 1, which means the x's are -8 and -1. Those two x values result in 0. So those are two more ordered pairs, -8, 0 and -1, 0. So having these 3 points is sufficient. You know it's a parabola, and there's the vertex, so that's the minimum, and you could just sketch a graph right here. But realize that the y-intercept is 8. If you plug in 0, you have a y-intercept of 8. So might as well plug that in, just as a further way to guide you. And then do your best to draw it out. The domain, it's a parabola, so it's always all real. But the range, this graphically, it's from -12.25 to infinity. But we knew that even before we graphed it, because we know that since there's a positive a value, +1, that means it's facing up. And if it's facing up, then it has a minimum. And the minimum y value is at the vertex. And every other y value is above this y value. Last slide. Without even graphing this quadratic, what do we know about it? First of all, the y-intercept is -3. If you plug in 0, you get -3. Second of all, a is -5. Well, since -5 is less than 0, this parabola is facing down. And if it's facing down, then it has a maximum value. And I could find the vertex. -b/2a would be -10 divided by 2 times -5, which is negative 10 divided by negative 10, which is 1. So actually, before I find the vertex, I just found the axis of symmetry is x equals 1. Plug that in to the function to find y, and you get 2. When x is 1, y is 2. So that means 1, 2 is the vertex. And the maximum value is 2, and that occurs when x is 1. Of course, it's the vertex, but again, I know it's a maximum because this parabola is facing down. And this is kind of interesting. Imagine the graph in your head. It's touching the y-axis at negative 3, but it has a maximum value of 2. So the max, the vertex, is above the y-intercept, you see. It's 5 spaces above this y-intercept. Well, that means that at some point, I must have crossed over the x-axis, right? That tells me that there are x-intercepts. There are real zeros. Again, because your maximum y value is 2, but you know you have a y-intercept of negative 3, so at some point you cross the x-axis, telling you that you've got x-intercepts. The domain, easiest question in the world. It's always all real. All quadratics have that domain. The range, however, we had to think about. Since it has a maximum of 2, the maximum is 2, every other y value must be below 2. So the range is, always read from left to right, from least to greatest, negative infinity to 2, including 2.